Hi everyone, and thanks for participating in NCSE's online course, Science and Language, Overcoming Controversy in the Classroom. I'll take just a couple of minutes to introduce both the course itself and our lead speaker today, Anne Reed. This course is designed to be helpful to a broad range of teachers, regardless of the grade level you teach or your specific content focus. If you deal with students and potentially controversial scientific concepts, this course will help you learn how to navigate controversy as well as navigate the scientific method. We'll help you learn skills to build dialogue with your students and create a more inclusive classroom. We'll help you identify and correct many common misconceptions about the scientific method. And we'll do some work in content knowledge related to evolution and climate change, which are two areas many teachers feel they could use a firmer background in so as to build their confidence in the classroom. To bring you great talks on these diverse but interconnected topics, we've recruited a number of different speakers. Starting us off for the very first in the online series is NCSE's Executive Director, Anne Reed. Ms. Reed has experience both as a research biologist responsible for sequencing the 1918 influenza virus and as an expert in communicating science to the public. She has served as the Senior Program Officer at the National Research Council's Board on Life Sciences for 5 years, and then most recently as Director of the American Academy of Microbiology. Since coming to NCSE in 2014, she has led our organization to work more deeply with outreach, engagement, and science communication. Please welcome her for our first online course module, Dealing with Controversy in the Science Classroom.
Thank you, Emily. And thank you to everyone who's listening online now. And hello, people of the future who will be watching this course later. I'm really happy to have you here and really happy to talk about these topics that I think a lot of teachers feel like they're left to handle on their own without a whole lot of support. And we think that if you stick with it through this course, you'll be able to teach these topics with, as Emily said, a lot more confidence. With that, let me share my slides, and we'll get started. So as Emily said, this course is really designed to help.
The slides yet? Let's try and pull them up again.
Uh-oh. So they're big on my screen.
Hi, everyone. Here we go. Let's see if that works.
Okay, can everybody see them now?
Yep, now we're ready to go.
Terrific. Okay, as Emily said, what we're hoping to accomplish in this class is to help maybe give you some background on why certain topics cause so much controversy in the science classroom and how you can deal with it. Now, in general, I think we all feel that science is shouldn't be controversial. I mean, it's just the facts, right? It's totally objective. It's not up for debate, and we don't get a lot of pushback when we teach about the periodic table or what the digestive system does. So that's what science should be, right? It's just dry. But no, it isn't always just the facts. It's not totally objective, and many areas of science are just not up for debate. They're not controversial in the scientific community at all. They are backed up by multiple lines of evidence, and the scientific community doesn't have any doubts about their essential soundness, but they face a great deal of societal contention. So I just want to say at the very beginning that science does, of course, have tremendous societal implications. Many, many scientific discoveries, many scientific techniques have ethical implications. They might have legal implications. We certainly want to regulate some kinds of science. And the political system is really responsible for deciding what we do with the results of scientific discoveries. That's completely appropriate. Societal debate should be robust about the implications of scientific findings and how we should respond to them ethically and politically. I don't want anyone to come away from this course thinking that science is not just one thread in our societal set of considerations that we have as we make decisions. And sometimes talking about those things is appropriate in science class. But that's not what we're talking about here. We're not talking about the political and ethical responses to these scientific topics. In this class, we're going to be talking about areas of science where people reject the accepted, established science that the scientific community has developed over decades, or in the case of evolution, centuries. These topics are in your textbooks. They're in the science standards. You are expected to cover them without any waffling. But sometimes that's really difficult. So how do you do it? Depending on where you're teaching, you're likely to encounter some pushback when you teach evolution or climate change or both. We know that sometimes dialogue, and in fact a lot of this course is going to be focused on how to expand dialogue in your classroom, that dialogue and debate can be very effective for getting students engaged. If you have a debate about whether evolution or climate change is scientifically established, you're going to really confuse your students. So that kind of debate is just inappropriate. But before you can address students' confusion about these topics, because you may well encounter that with students or parents or with even your administrators or school boards, it's important to know where that confusion comes from.
Now, if we can pause for just a moment for questions. I have a question from a teacher here where, what if students ask questions because they're used to hearing, especially climate change, presented as a debate?
So,
like what if students want to handle this as a debate? How do you respond to that?
That's tough because, as we said, debate can be, it can really get kids engaged. But in this case, it's important to establish that there are some things that we don't debate in science class. We don't debate gravity. We don't debate we don't say sodium, are you for it or against it? It's there when the scientific the scientific theories are well established. It's not appropriate to open them up for debate. That's just going to confuse your students. And later sessions will go into much more detail on what the distinction is between a good dialogue and an inappropriate debate.
Nice. Now, for all of our participants, I want to remind you that you can send us questions throughout this talk by using the chat bar on the side of the Google Hangout if you're tuned in that way. You can use Q&A installed if you have that app on Chrome, or you can tweet us at NCSETeach. So back to Anne. Thank you.
Okay. Any other questions? Okay, so let's talk about why evolution and climate change in particular seem to cause so much confusion. They're not the only topics where there's this kind of disconnect between what scientists believe to be well established and what the public accepts. It turns out that science just isn't always about science. And even scientists don't know everything. I hate to admit that, but we don't. We know a lot about our particular area of science. We don't know the details of other areas of science. All of us look to many different sources of information to make up our minds about things, and scientists are one of them, but they're not the only one. So on the left of this slide, I pulled up a bunch of pictures of sources that people might go to if they were trying to decide whether it was safe to vaccinate their kids. So we see a pediatrician. We see a grandma. Certainly people might ask their own parents what they should do. We see friends talking to each other. Certainly people lean on their friends to figure out what to do. And then the two other little pictures there. One is the CDC, the Centers for Disease Control and Prevention, which is the government agency responsible for public health. So they have a great deal of information on not only vaccine safety, but all kinds of information about healthcare, the evidence base for healthcare decisions. And then above that, what says Vaccine Safety Manual, that's kind of the red alert, because that is actually a vaccine safety denial website. And as you can see, it looks very sophisticated, very legitimate. It's got a nice family there, and it says it's for concerned families, and so it can be often really difficult to tell the difference between a legitimate source of information and an illegitimate one. So you see all of these sources. How do you decide which to trust? Does anybody have any other sources that they might go to for vaccine safety, or any experience with these kinds of conversations?
I just want to interject for people who haven't looked at it. The CDC's website is fantastic for just everyday use. The CDC puts out really clear pamphlets on vaccine information as well as all types of other infectious diseases. I really enjoy using it personally.
Yeah, it's really great when you're raising kids and you have a lot of questions about what might be going on. You often forget to ask the right questions at the doctor's office, and the CDC can really fill in those blanks. And it is really accessible. I think even middle school students would find a lot that they could navigate there.
They also have very good maps for people who, like me, love to look at maps.
Yeah, they've got awesome epidemiology stuff. Okay, enough nerding out. Here we go. So the way scientists go about deciding what they think about a particular topic is quite a rigorous process. All scientists are trained to approach asking questions and gathering evidence and evaluating the results of their work in a way that prevents them from fooling themselves, I think is the best way to say it. And that will come up again when we talk about science misconceptions, that the ideal is to set up your work in a way that you don't know how it's going to turn out, and the way it turns out informs what you think about how the world works. So that approach is common across all of the sciences. It manifests itself differently if you're a theoretical physicist versus if you're an ecologist, but that general approach that you frame your questions in a way that you can gather evidence that answers that question and no other is in common. And because that process is in common across all of the sciences, scientists generally trust what other scientific communities conclude. So it doesn't mean every scientist believes whatever any other scientist says. I don't want that to be the confusion, because all scientists also know that we all get things wrong sometimes, and so any individual scientist's conclusion may or may not hold up in the long run. Not that it would be wrong or fake, but that it might be incomplete, and so the interpretation of it may change over time. But if an entire field of study has come to some conclusions about the way a major process works, and that many lines of evidence have contributed to that conclusion, so in the case of climate change, you have atmospheric science, you have oceanographic data, you have ecological data, you have satellite temperature measurements, you have all manner of different kinds of scientists who have all looked at these questions, and they've all come to the same conclusion that the planet is warming and human activities are responsible. When other scientists see tens of thousands of scientists coming to a common conclusion, they tend to trust it. So, but I do want to say that scientists trusting scientists is a specific example of what we all do, which is we turn to the people we trust to make decisions about what we're going to believe. So scientists trust scientists, but that doesn't mean that everybody else goes to scientists as their first source of information about what to accept. So I love this work that was done by a professor of behavioral psychology at Princeton. Her name is Susan Fiske. And she did a huge survey of people, asking them about all different kinds of professions. And she asked them, for each of these professions, how competent do you think people in this profession are? And how warm do you think they are? And she graphed the results here on this with the y-axis representing warmth and the x-axis representing competence. So you can see that all of these different careers, and so this is the average of everyone's responses, that people have preconceptions about what people in these different careers are like. So, okay, I was looking to see if I had a slide where I had some arrows on here, but maybe, can you see my mouse? Or not?
Yes, we can see your mouse.
Okay, so my mouse is over here pointing at scientists. And as you can see, the only people who are considered, more competent than scientists are engineers, just a teeny bit more. So this is good news for scientists who would really like people to think that we know what we're doing. So that's great. But look at this. Look where we fall on the warmth scale. Uh-oh. I left my screen. Are you guys also seeing this?
Everything normally. Everything looks good still.
Okay. So if you look over here at the warmth scale, scientists end up somewhere between office clerks and bus drivers. So Minda's coming in to save me again.
I feel like I've had many very nice interactions with bus drivers. I feel like they're being maligned unfairly on this slide.
Well, obviously, apparently people, some people have had good interactions and some people have had bad. It may depend on where you're from. But in any event, we don't see scientists up here with people who are generally, on average, considered much warmer: nurses, child care workers. I think this is really interesting that farmers are considered very warm. And doctors and professors also end up higher than scientists. I do want you to take note, all of you teachers, that you are in a very privileged position here. You're considered quite competent and extremely warm. So the importance of being considered warm is that you trust people that you feel empathy towards. And so this being in this circle here, where you're not considered very warm, look who else is in this circle with the engineers and the scientists: lawyers, CEOs, people who, sure, maybe they're good at what they do, but I'm not sure that I really trust them. So this not being particularly warm is a problem for scientists and engineers who are trying to convince people to accept their conclusions. But teachers, you guys are in a great spot. You have the possibility of being very convincing to people and of gaining their trust. So that's really important, and it's a great responsibility. The other people, the other groups and sources that people look to for their information when they're trying to decide what to think about something controversial, they may look to their religious leaders and their religious congregations. They may look to political leaders. They certainly look to the news media to see what is being said about these issues, and they very, very definitely turn to their friends and neighbors to find out what they think about these issues. Students look to different people over the course of their lives. They look to their parents when they're young, maybe not so much by the time they get to high school. They start looking to each other, but they always look towards their teachers. So again, this puts you in a really strong position for dealing with these topics. I just want to dig in a little bit to the importance of the community that people come from. This may be very relevant to some of you, depending on what communities you teach in. When it comes to teaching evolution, the discomfort with evolution, the rejection of evolution, is almost entirely religious in nature. People who reject evolution instead believe that God created all of life's biodiversity, and they believe that evolution means that you don't believe in God. So they have a real dichotomy in their mind that it's either believing in God or it's believing in evolution. That's one of the things that you'll learn in other sessions that will be a very important misconception for you to put out in the open and disabuse. But this National Study of Religion and Human Origins, which is in your reading materials, asked people why they held these beliefs, why it was important to them to hold these beliefs, and what kinds of communities they lived in. And they found that creationists are much more likely to live and be friends with and be in families that agree with that who reject evolution. They often don't know anybody who accepts evolution. They also feel that if they did accept evolution, it would really cause them problems with their families, their friends, their congregations. Their congregations often have explicitly said that evolution should be rejected on religious grounds. And many of them have never had any real scientific training in evolution. It has been skipped or glossed over or denigrated in the science classes that they took. So community matters, and community matters for climate change as well. But that religious basis of the evolution rejection is really strong. So where people get their news matters a great deal too. This is based on another Pew Research poll that asks people where they get their news, and they cross-correlated that with how these people can characterize themselves politically. And you can see this tremendous difference that people who are consistently liberal, these are the top 5 sources of news for them. It's quite diverse. There's no one overwhelming source of news that they all listen to, but you will notice that Fox News does not appear in the top 5. Whereas for consistently conservative individuals, almost half of them get the majority of their news from Fox, and then a minority from other sources. So as you know, if you've ever listened to NPR and Fox News on the same night about a particular issue, you might feel like they're not reporting from the same planet. It's so very, very different. So it's not at all surprising that people who get all of their news from one of these sources or the other are going to have very different views on certain scientific topics, and that is very much the case with whether they accept the science of climate change or not.
So before we move on, we have a couple of questions, and just as a reminder to people who might want to ask questions, you can write us through Google Chat if you're on the Hangout. You can tweet us at NCSE Teach, and if you're having trouble with either of those, you can reply to the email you received that lets you join this online course. So we have a question from a teacher relating a scenario that occurred in their life. This teacher says, I had to deal with students who were coached at their church to ask, one at a time, to be excused from my class when controversial issues arose. This created maximum havoc in the main office and, as you might expect, an instant lack of support from the administration. I eventually landed in both common pleas and federal courts. What would you recommend in a situation like this?
I would recommend that you call NCSE. We have a lot of experience helping teachers deal with situations like that. That's a lot for one individual to take on. You're going to need community support. You're going to need some advice on your legal standing, and I admire you for sticking with it because I know it's really difficult. But yeah, I think that at that point you need to call in the troops. You do need to be aware that you're absolutely correct to stand on your right to teach evolution, and that most states don't allow students to opt out of that class. So you're on solid ground, but you're going to need help, and we can provide it.
I think it's really good to try and let as many teachers know that help is there. I think that from my work in Iowa, a lot of teachers have no idea that there is help if you start having to deal with this sort of really uncomfortable, really emotionally draining controversy in your school and in your community. As another question, we have a question from another teacher asking, has anyone tried having students look at different news sources to see if their opinions on these topics change?
So yes, teachers have certainly worked with students to look at different sources of news, and specifically from a science class point of view, to help them learn how to ask the right questions about the sources that they're going to. So there are people who've developed exercises of, okay, I want you to go to these 5 websites, and I want you to figure out where they get their funding, what is their point of view, who benefits from their interpretation of the science. That can be very powerful, and certainly it's a life skill that we want all of our kids to be able to leave school with, that they can look at the information that they find on the internet or that they hear on the news with a certain amount of informed skepticism. But you do have to be careful that you're teaching science, you've got a whole lot of material to get through, and you don't want to get sidetracked into turning these topics into a debate-ish approach where, you know, some people are saying that they agree with this source and some people are saying that they agree with that source. So it's not a bad idea, but it has to be done with considerable care.
If I may interject, this is often a really good activity to team up with your librarian about. This sort of news access and source evaluation. A lot of librarians have specialized training to help students with this. And I know that throughout my education, when we had librarians come and work with our science teachers to help us learn how to evaluate sources, that helped to all of us to develop a lot of life skills that were useful moving forward.
That's a great suggestion. Do you have any more questions at this point?
No, we're ready to go.
Okay. So just to reiterate again that in these cases, people's opinions about climate change or evolution are not about the science. It's not that these people are ignorant and poorly informed. The reason that it's so important to just hammer on that point is if you think that just teaching them lots of science will change their minds, you are likely to become quite frustrated. I'm sure that teacher who had the organized church opposition to evolution would second that firmly, that people are rejecting these scientific conclusions because they conflict with something that they hold very dear, and that where they feel that accepting those scientific conclusions is just in complete contradiction to who they are and what they believe in. As we showed, that this can be a religious objection for evolution. It may be ideological for climate change. It may be economic if you fear that climate change means your state's economy is going to crash, or you've been told that. Or it may be about more libertarian values, that you just don't want the government interfering, and so you feel that climate change is just an excuse for government to do that. You're going to hear all kinds of different sorts of objections to climate science, but none of them are really based in the science. I just want to tell a little story just to show that this is something that we all do, and so looking down on people who reject these areas of science or assuming that they do it because they're not that bright is a real mistake. I have a very good friend who is herself a very competent scientist, and she moved to San Francisco for a job, and she was sharing a house until her husband moved out with another woman. And that woman had one night said, "I don't know whether I'm coming home tonight or not, so if you hear, you know, if I do come home, it'll be in the middle of the night." Okay, fine. So she went to sleep, and she woke up in the middle of the night, and she heard noises. And she thought, wow, I guess she's home, but boy, she sure is making a lot of noise. That's not like her. But it was 3 o'clock in the morning. She was barely awake. Then she heard cabinets and drawers being opened downstairs, one after the other. And she thought, wow, she is really making a lot. What in the world is she doing down there? That's really strange. And then she heard someone coming up the stairs, and she started hearing all of the doors in the hallway being opened, the bathroom, the closet, and then her bedroom door. And you can imagine what it was. It was of someone who had broken into the house and was burglarizing it. And you know, she screamed, and the person ran away, and you know, the rest is a story of the police coming. But what stunned her is that she had all that information that this was not her roommate coming home. She had heard all kinds of things that suggested that this was not her roommate, but her brain just could not wrap itself around the fact that it wouldn't be, because she was so sure it made so much more sense that it would be her roommate coming home. So I think we all, if we think about our lives, we can think of situations like that where reality sort of didn't make a dent in our preconceived notion until we really had no choice. So just as a matter, again, of developing warmth and empathy, remembering that that's what's going on when science is being rejected will really help you approach people with these issues with more understanding. So recognizing that these topics are going to make people uncomfortable is very important. Remembering that you are in a really privileged position. You are trusted to give the straight scoop, and that means that you have an opportunity to say in a context where you will be trusted that there are different ways to understand the world, and science is one of them, and science has a specific way of understanding the world. It's a powerful way of understanding the world, and that's what you're going to be teaching your students in the class, that this will be a way of looking at the world that will give them power throughout their lives. And it's something that not only scientists can do, but they can do too. When you do come up against these different worldviews, you don't have to have a debate. You don't have to go at them head on. Instead, you can, again, be clear that what you're doing is showing how scientists approach these issues, how they gather evidence, how they reach conclusions, and your students are going to learn to approach them the way the scientists do. Again, with evolution, the issue is almost entirely religious, and there are certain misconceptions about evolution that really reinforce that conflict between believing in God and believing in science. One of the top ones is that people think that evolution says that humans descended from apes, that humans are not special, that humans are just monkeys. That's very threatening to a lot of people, and it's not actually correct. It's not really what evolution says. So when you get to teaching about human evolution and you can talk about why that particular misconception is incorrect, you're coming at this conflict between their religious beliefs and evolution in a sideways manner rather than head on. So I left a space here for the possibility of people thinking of other misconceptions about evolution that really cause a conflict with people's religious beliefs.
Well, you know, we don't have any particular questions on this topic coming in, but I think that when you look across the scale, not just at particular branches of Christianity, such as the modern evangelical movement, but into other religions, like Islam, which is generally more accepting of evolution, your real problem comes in when you're dealing with human origins.
That seems to be the part of evolutionary theory that is most concerning to people of a more fundamentalist religious faith. But there are others. I'd give the example of this misconception that evolution is completely random, and that it comes about by one individual mutation in DNA at a time, and that is hard. It's hard for people to imagine how you could end up with the incredible biodiversity we have around us if it had to happen one accidental mutation at a time. So that's another piece of misunderstanding about evolution that can help people think, just like my friend thought that her friend was making a lot of extra noise rather than realizing it wasn't her friend. That if that's what you think, if that's how you think evolution works, then it's much easier to think that it doesn't really explain the evidence.
It can be very difficult, too, to picture the amount of time that life has existed, the amount of, you know, the geologic scale of time, the vast amounts of time over which evolution has occurred. related to biodiversity. I think that that can be difficult to grasp for people.
Absolutely. Yeah, we don't really think in billions of years very easily.
But, you know, when we are talking about these misconceptions, if you're having trouble thinking of them, probably because as a viewer you have a perfect grasp of evolutionary theory, we will help you to understand other people's potential misconceptions in an upcoming lecture in this series.
Yes, we'll go into a lot more detail about these misconceptions and how you can. So I think that's a great point, Emily, because a lot of times if you yourself do have a good grasp of the science, it may be hard to even imagine how someone could have it wrong because it seems so clear. But these misconceptions are extremely widespread, and they're hard to root out if you don't go at them directly. So we will talk a lot about how to do that so that your students don't leave class with those misconceptions still hanging about. In fact, in that class, we'll also talk about the way that those misconceptions are very regularly reinforced in the media. So that's an excellent teaching tool to show some articles that that misrepresent evolution that way and have the students be able to say, oh, wait, that's not right, because we already know that missing links is not a good way to think about evolution. So that those misconceptions that show up in the media can be a great teaching tool. With climate change, again, it's not primarily a religious issue when people reject climate change. In fact, there is a fairly robust religious movement called Creation Care that believes that we have a responsibility to be good stewards of our planet, and therefore that responding appropriately to climate change and helping the people who are affected by climate change is a very important religious responsibility. So generally speaking, this doesn't break along religious lines, but it does break along political lines that people who identify as conservative, people who get most of their news from Fox News, people who think that the government should stay out of people's lives are very likely to reject the scientific evidence that the climate is changing. In many cases, when you really dig down into what the problem is, it's that they're really afraid that if that science is correct, we're doomed, and there's nothing that we can do about it, and so they just refuse to accept it, much as my friend refused to, her brain just refused to accept the idea that there might be a burglar in the house. It's much, much more comfortable psychologically to just say the scientists are making it all up than to accept that we have this really serious problem to deal with. So again, just as with evolution, though, misconceptions about the science itself or about the way science works can really reinforce that mindset. For example, many people feel that science is a set of facts, and that science is either right or wrong. And when you look at a lot of climate science, especially climate models, which are an area that can be particularly thorny for people, the models give a range of possible outcomes. The temperature may rise by 2 degrees or it may rise by 4 degrees, and the level of uncertainty is whatever, 70% or 30% or 2% or whatever it is, but it's going to rise 2.5 degrees and it's going to happen in 2078. And if people have this misconception that science is, once you discover something in science, it's undisputed and it never changes, that kind of probability-based evidence can really be hard to accept. Can anybody think of some other examples of people's misconceptions about the way science works that reinforce the idea that climate change science is not trustworthy?
We've got a participant here who says that they run into the misconception frequently that the sun is the only thing responsible for climate on Earth.
Right. That's a good one. And I think that will be one of the misconceptions that is discussed when we get into common misconceptions about climate change. Is that right, Minda?
Yep, it looks like Minda will be discussing that. And Minda also interjects that The misconception she frequently deals with is that climate change relies on a few faulty models instead of a wealth of evidence from multiple fields. And that's something that I've encountered too, is that people don't know how many fields of research feed into the evidence for climate change right now.
And that is also a great teaching tool. And that's true for evolution as well, that evolution, you know, there's sometimes you get the impression that people think that Darwin thought of evolution and that's it, and it hasn't changed since what he said, and don't realize that evolutionary biology plays out across every single field of biology, and even into geology and some of the non-biological sciences, that you can find evidence of evolution in the DNA and in the developmental pathways that that organisms take, and its similarity between the regulatory networks that work in yeast and also work in humans. That you've got the fossil evidence. You have again thousands and thousands and thousands of scientists in dozens of fields that have all found evidence that mutually reinforces the reality of evolution. And climate is exactly the same. It's sometimes interesting to ask people, how many climate scientists do you think there are in the world? And it's sort of a trick question because, as we just said, it's not only people who identify specifically as climate scientists who are finding evidence for climate change, but the numbers that you get will be really shockingly low. And it's often useful to say, well, you know, the American Geophysical Union, which is the scientific society for scientists who work on this area, has over 50,000 members. And not every scientist belongs to the scientific society. This is a really, really big group of people, and that's only the people who look at it directly as climate science. So, and the same with evolutionary biology.
Yeah, I think that a lot of people wouldn't know that, for example, a lot of biologists are contributing to climate change research, that a lot of biologists are studying how organisms' habitats are changing and shifting related to climate change. I think that many people find science related to animals to be accessible because animals are both interesting, they're relatable, and often they are cute. So there are a lot of very accessible research studies that provide evidence for climate change out of organismal biology. And just one more plug for how to ask questions. Don't forget, you can tweet us at NCSE Teach. You can write into the chat window on Google Hangouts, or you can respond to the email that invited you to this talk.
Just one other example of this misconception that somehow science is what you find in the textbook, not that science is an ongoing activity, that helping your students do science themselves, and that doesn't necessarily mean in a lab. It can be a thought exercise. For example, to ask them, okay, let's assume that climate change is happening. What would you look at to demonstrate that to yourself? For example, show them the USDA zone map that you use to plant your garden to decide whether a particular shrub or a particular vegetable is going to grow in your yard. The USDA publishes that every 10 years. Show your students one of those and say, okay, if climate change is for real, what would happen to this chart in 10 years? And have them think about it. What would they look for? How would they convince themselves that the climate was changing? What's really spiffy about that example is that if you look at the last 4 maps from the USDA, all of the zones are shifting northward and upward in altitude. So it's extremely visually compelling that the climate is definitely changing in this way that people can really understand.
As an additional resource that I'd like to plug for other people who love birds, maybe not as much as I love birds, but who love birds, the Audubon Society has a wonderful visual interactive website that shows the projected migration changes for migratory birds. And you'll see that those are all consistently moving northward.
Yeah, ecology is really a very accessible way for people to get into climate change. So we'll be talking a lot about that throughout the course.
Oh, and we have an interjection from Minda that she's going to use that resource in her session. So she'll show you all how to use the Audubon's resources. But I'll stop interrupting now.
Awesome. So just to reiterate, how is this going to affect your classroom? And the take-home message is to remember that every student who comes into your classroom is going to have some misconceptions about science. Probably especially they're likely to have misconceptions about these societally controversial areas of science like evolution and climate change. And they're all going to have preconceptions about how the world works. But they're not alone. It's not just your students. You have these misconceptions too. So do parents, so do administrators, school board members. We all do. So just a little bit of sympathy towards everyone, and a little extra antenna up for seeing where these misconceptions might crop up in different people. So, often science is sort of a privileged space where we don't have to worry about that because much of science is so uncontroversial, and there isn't, as I said at the very beginning, we don't get a lot of pushback on teaching the periodic table or the structure of atoms or F equals ma. Nobody is out there shouting that that's a terrible thing to think. But there are these topics, evolution and climate change primarily, that do have these really quite deep conflicts with what people believe about the way the world works. And if you don't know that those attitudes and misconceptions are lurking in your students' minds and in their parents' minds and perhaps in the community's worldview, you may well miss an opportunity to have your students cut through those misconceptions and understand a little better about how the scientific community came to the conclusions that it did. So I'm just going to give a really 10,000-foot level overview of what you will be doing, and this will be made much more explicit in the upcoming sessions. But as I mentioned with evolution, you can design your approach to teaching evolution or climate change knowing that some of these misconceptions are going to be pretty deeply embedded in your students' minds coming in. And you can address them in a way that helps the students recognize that their misconceptions are getting in the way of understanding the science. So we'll approach that in three ways. First, the misconceptions that people have about how science works in general, and then about climate change and evolution in particular. And over and over and over again, you're going to hear two key suggestions. One being, make it as personal as you can, and the other being, lead with the data and let the students ask the questions and work with the evidence and come to their own conclusions, just like scientists do. So with respect to bringing it home, as we were just saying, use examples that students can relate to, and often ecology and birds and plants and local conditions are going to be things that students can relate to and that they can go out and measure themselves. They can measure temperatures themselves, they can measure rainfall, and they can look at long-term rainfall trends for their own neighborhood. They can look at the historical records of when certain plants budded in their region, the frost dates in the fall and the frost-free dates in the spring. They can look at the agricultural data on when certain crops are harvested. And of course, the Audubon Society does these awesome Christmas bird counts that are very local and that students can actually go out and do for themselves. There are also examples that may not exactly be local, but that are relatable. For example, antibiotic resistance, that most students know about, but may not understand that it's an evolutionary process. And teaching how evolution leads to antibiotic resistance is a very powerful way of helping students see how evolution works. invasive species. And again, these USDA plant hardiness zones are very easy to relate to examples. And then you can really encourage your students to go home and talk to their parents and to their, especially their grandparents, about the weather when they were children, about the perhaps they may well have experienced certain crops were much more common when they were kids and that they don't grow in that area anymore. That's how quickly the climate has changed. It has happened in a lifetime. They may talk to local farmers about new crop varieties and why they grow better than the old ones. Those are really great evolutionary science examples. How to reduce pesticide resistance, again, is an example of evolution. They can look at the patterns of severe weather events in their area, whether it's an area with tornadoes or with floods or with droughts. They can look themselves at the evidence for the increasing frequency of those events. And then so that's sort of the flip side of give them real data to work with. Both evolution and climate science, we've already talked about this, they rest on a lot of different kinds of data that many different kinds of scientists work in these areas. And if your students are exposed to ecological evidence for climate change, marine biology evidence, and the climate models, and atmospheric chemistry, and ocean chemistry, like acidification, you end up with an accumulation of evidence from all of these different areas where it becomes much harder to say, I reject climate change because this one study was wrong, or because I don't think models are reliable, because they've got this buildup of evidence from all kinds of different fields that reinforce the conclusion that the scientific community has come from, that this is really happening. When you come to debating, this is a great place to really start having dialogues about what does this data say? What is the evidence for the conclusion that you're testing? Encourage them to do that, and that's a great group activity. And the bottom line there is that you're not standing up in front of the class and saying climate change is real. You are giving them the tools to come to that conclusion themselves, but because of the exploration of the data that parallels how scientists have come to these conclusions. That will have benefits down the line, not just in their likelihood of accepting climate science, but misconceptions about other areas of science down the line, that when something like vaccine safety comes along, or is organic food healthier than non-organic food, or are GMOs safe to eat, that hopefully the seed will have been planted, that they recognize that scientific evidence is a particular kind of evidence, and evaluation of that evidence has rules and practices, and that they should be thinking about, where's the evidence for both sides of what looks like a debate. And when they learn that the scientific community is united on one side, then that hopefully they will remember that is based on a lot. It's not just a trivial thing for the scientific community to come to a consensus opinion. So we have just a few minutes for open-ended questions, and I hope that this will give you a flavor of what you're going to be learning over the next set of classes.
Well, thank you, Anne, for this great talk. I just want to remind people that we are going to be having an upcoming series of webinars. There's going to be 5 more in this series, and we'll send you emails to know when those are going to be. They'll be in the evening, which hopefully will be more convenient to allow us to reach a wider audience, and we'll be hosting these on our website so that really you'll have the chance to watch them at your leisure if you're not able to tune in live, so that you can ask questions. So let's see here. It looks like we don't have any questions at this time, but if you'll tune in our upcoming seminars, we're going to be talking about concrete strategies for using language to build dialogue in your classroom to help people work through these controversial topics. We'll be talking about content misconceptions and process misconceptions. We'll be talking about the scientific method and the language of the scientific method. And we'll be dealing with controversies that teachers have and may encounter in their classrooms. So thank you again, Anne, and thank you all for participating.